In this lecture, I will show you a simple, straightforward logic, namely Hennessy-Milner logic. Here we see the pictures of Robin Milner and Matthew Hennessy. So Robin Milner is a person that we have already seen a number of times. Matthew Hennessy was a PhD student of Robin, and they together made what's currently called the Hennessy-Milner logic. And their purpose was to characterize strong bisimulation with a logic, and they came up with this particularly elegant solution for that. So what's Hennessy-Milner logic? And I present the syntax here using Backus-Naur form. So a formula can either be true, and true is the logical formula that's valid in any state. It can be false. False is never, ever valid in no state. We can use the negation, the and, the or, well known from logic. And we have two special operators, namely the diamond modality, A phi, and this says that you can do an A in a particular state, after which phi should hold, and the box modality, and that says that whenever you do an A in a particular state, phi should hold afterwards. So, when is a Hennessy-Milner formula valid? So we take a formula and a state, and we say that this formula is valid in a particular state. And often we do not mention this state explicitly, but then that's generally the initial state of the system that we consider. So we can say that true is the formula that's valid in any state. False is the formula that's never valid for any state. If we know that phi is not valid in a state, then not phi is valid in a state. And in the same way we can say this for and. If we have the formula phi1 and phi2, then this formula is valid if phi1 is valid in this state and phi2 is valid. And reversely, for the or, phi1 or phi2 is valid in a state if either phi1 is valid or phi2 is valid. And of course, they can also be both valid in that state. And we also have the two modalities, the diamond modality and the box modality. And I will spend the next slides on explaining these. So we have the diamond modality. And this says that so A phi is valid in a state S if there's a transition from S to a state S prime, an A transition, such that phi is valid in S prime. So typically, if I have a state S, and I want to make this formula diamond A phi valid in S, then there must be an outgoing A transition to a state S prime, where phi is valid, and that is enough to make diamond A phi valid. And it can be more complex. We can have a state with an outgoing A to a state where phi holds, and then already diamond A phi is valid, but there can also be more outgoing A transitions to states of which we have no idea whether phi is valid, and there can even be outgoing transitions labeled with other actions than A, for instance B, and they are of no concern for our modality A phi. Okay, so let's look at this small example. If we write down diamond A, diamond B, true, is this, what does this express? So what it expresses is that you have a state S, and in this state S it should be possible to do an A, and then you end up in a state where B true must hold. So from this resulting state we have to be able to do a B. And then we end up in a state where true must hold. Well, true is valid for any state, so that doesn't put any other requirement anymore. It can be that we have more transitions, and that does not really matter at all. It's enough that we can do an A and a B from the state S. So actually what we say is there is a trace AB from state S using this modal formula. We can also look at this modal formula where we say diamond A followed by diamond B true and diamond C true. So what does this express? Well, let's try to understand this in terms of a label transition system. It should be possible to do an A, where B true and C true should hold. And that means that we should be able to do a B from this resulting state and a C. And this is enough to make this modal formula true. We can also change our transition system a little bit. Take these two outgoing A's from the initial state and ask ourselves whether this modal formula holds for this transition system. Well, what we see is that we can do an A from the initial state, but then we end up either at a state where we can do B or at a state where we can do C, but we don't have a resulting state where we can do both a B and a C. So what we see here is that this modal formula is not valid for this transition system. We can change the transition system a little bit by adding an extra B to the right branch. And what we see here now is that we have an A transition going to a single B, but this does not help to make this modal formula true. But we have also an A going to a state where we can do both the B and the C, so in this particular case, the modal formula is also valid. And this is what the formula expresses, namely there is an A after which a B and a C are possible. So we can also look at the box modality. So the box modality is valid in state S when for every A that you can do, phi holds afterwards. Or put in other words, for all states S prime, such that we go from S with an A step to S prime, phi should hold in S prime. So, expressed in a transition system, if we have a state S and we have only one outgoing transition A and phi holds after doing the A, then box A phi is valid. And if we have a state S and we have more outgoing transitions, after which phi is valid, so for this one and for this one, then we can say that box A phi is valid. And it doesn't really matter if we have other transitions than A transitions, so generally I'm not even considering them. They are irrelevant for this formula. There's one special case where box A phi is valid, and that's this case. If I have only a single state without any outgoing A transitions, then A phi is valid. Namely, for all outgoing A transitions, and there are no outgoing A transitions, phi holds at the end. And you can see that independent of how phi looks, this formula is always valid for any transition system, of any state without outgoing A's. So let's look at a few formulas with box modality. So if we have box A, diamond A, true as a formula, what does that mean? And take just to understand this transition system with two outgoing A's and this not so relevant B. This says that if I do an A, I end up in a state where diamond A true should hold. So after doing any A, I must be able to do yet another A. So an A should be possible there, and an A should be possible here. And that is exactly what it says. It says, after any A, another A can be done. Okay, look at this example. And this is an example that you will see more often. What's the meaning of box A false? Well, if I have a state with an outgoing A transition, then what we see is that after this outgoing A transition, false should hold. But we know that false does not hold in any state. So if there's an outgoing A transition, we have an impossible situation. And there's only one way to make this formula valid, and that is by forbidding that an A can be done. So actually, it's only valid in a state without outgoing A transitions. And this is the meaning, namely, box A false is valid in a particular state if an A action is not possible in that state. Okay, let's look at a number of exercises. If we have this modal formula consisting of 5 times diamond A, when does this formula hold in a state S? Here we have the second exercise. If you have the formula diamond A true or diamond B true or diamond C true, when does this formula hold? And I give 4 possibilities. And now this third exercise, we have box A, box B, box C, false. What does it express? Or differently, when is it valid in a state S? Okay, so what did we do? We introduced Hennessy-Milner logic. And with Hennessy-Milner logic, we can express elementary properties of labeled transition systems. And the Hennessy-Milner logic consists of the standard logical operators from propositional logic. And we have 2 modal operators, namely the diamond modality, diamond phi, and the box modality, box A phi. In the next lecture, I will show you a number of identities among Hennessy-Milner formulas. Thank you for watching.